Hi guys, welcome back to my YouTube channel. So today we'll be discussing on conduction mode of heat transfer. So we've discussed, you can check my previous video, we've discussed on what heat transfer is and the modes of heat transfer that we have. So today we are moving to conduction. So and conduction uses the Fouriers. So we've established the definition of conduction. Then conduction uses the Fourier law. And what does our Fourier law state? States that the time rate of its transfer through a material is proportional to the negative gradient in the temperature and the area. So the mathematical expression is this. They said the time rate, which is Q, of its transfer through a material is proportional to the negative gradient. This is the negative gradient. That means delta T over dx in the temperature and the area, then the A. We're having negative because temperature decreases across the heat. So unlike as the heat increases, temperature decreases. So that's why we're having our negative. So our Q is the rate of heat transfer or flow by the conduction. We are talking about conduction. So, and it's usually in watts. Our K is the thermal conductivity, which is usually in watts per meter Kelvin, which depends on the nature of material and its temperature. So this K is not like a constant. Yeah. So it depends on the material, the nature of the material and temperature of that material. So A is the cross-sectional area, which is a meter square, and our dt over dx is the temperature gradient, which is in Kelvin per meter. So we also have our heat flux, which is small q, and it is defined as the rate of heat transfer per unit area. And the formula is the unit is watts per meter square. So since they said it is the rate of heat transfer, which is our q per unit area, which is q over e, which is going to give us minus k dt over dx. So we have different modes or different materials in which conduction can take place. So it can take place through a plane wall, it can take place in a composite material, it can take place in a cylindrical wall or shape rather, or a sphere. So we are going to take note of each of these places in which conduction can take place. So continue. If you are just stumbling on this page, please do not forget to subscribe, like, share this video to people that you know that this video is going to be helpful for. So let's continue. So now we're talking about conduction through a plane wall. So now we are considering a plain flat wall. Let's say this is the wall, and it is going to like transfer. It is going to flow through this wall. So this is the initial temperature, and as it flows, temperature decreases. So this is our out phase or the inlet temperature, then flows through to the outlet temperature. Then this is the thickness of the wall, which is our x. X is the thickness of the wall. Then we are assuming that our K is independent of temperature and area of wall. So now our Q of plane wall is Ka into bracket T1 minus T2 all divided by X. Now our K is our thermal conductivity, our A is the area in meter square, our T1 is the inlet temperature or the inner temperature, our T2 is the outlet temperature or the out what's it called, out temperature. Then our x is the thickness of the wall. So when we rearrange this equation, we have T1 divided by T1 minus T2 divided by x over Ka. Now this x over Ka is our thermal resistance, which is R. Now we can now say our Q is T1 minus T is our change in T, then divided by R. Do you understand? So this x over K is our R. So we can say R equals to x over K. So therefore, our Q is not delta T divided by R of wall. So, and conductance is 1 divided by R wall. So each flux in Q, we mentioned earlier, there is the rate per unit, it per unit area, which is Q. Right, so that these are the formulas that we'll be using to calculate conduction through a plane wall. We have our R, we have the Q, we have Q in terms of the thermal conductivity, the area, temperature difference, and the thickness, and we have Q in terms of the temperature difference and the thermal resistance. And we can also be asked to calculate our conductance, which is 1 over R, or we might be asked to calculate our heat flux, which is Q divided by A. So let's get right into the first question on conduction through a plane wall. A brick wall has a thermal conductivity of 0.72 watts per meter Kelvin and is 0.3 meter thick. The inner surface temperature is 40 degrees C. The outer surface temperature is 20 degrees C. The wall area is 10 meters square. Find the rate of heat transfer through the wall. So when solving calculations on conduction, especially when it has to do with wall, I like to put it in diagram so as to understand the question very well. And like I always say, when you have a question, the first thing that you should do is write out your parameters and what you are looking for. So now, solution. We're giving our, okay, so they said we have a brick wall. So let's say this is our wall. It has a thermal conductivity. Let's write our K here of 0.72 watts per m Kelvin. Let me increase the wall. So let's say this is our wall, watts per mk, and it's 0.3 meter thick. That is the thickness of the wall, 3 meter, 0.3 meter thick. The inner surface temperature, I mentioned that this is where the inner surface temperature will be, so which is our T1, is 40 degrees C. 40 degrees C. The outer surface temperature is 20 degrees C. You know they said that temperature decreases as it increases. Can we see now? Yes. So from 40 we went to 20 degrees C, so which is our T2, 20 degrees C. Then we're giving our area to be 10 meters square. We have to calculate Q, which is the rate of its transfer. And since we know that the formula for calculating conduction of a plane wall is Q equals to Ka C1 minus T2 divided by X. So we have our K, we have A, we have T1, we have T2, and we have our X. So all we need to do is input our values and we get our answer, which would be equals to 0.72 multiplied by 10 multiplied by, what's our T1, 40 minus 20, then divided by X. What's X now? 0.3, that's the thickness of the wall. So what's this going to give us? So we have 480 watts, and we've calculated our Q. So that's that about this question. As you can see, it's not much of a big deal. So let's just quickly run through it again. A brick wall has the thermal conductivity of K. So we assume this is our wall. Then it is 0.3 meter thick, the thickness of the wall. The inner surface temperature is 40 and the outer surface temperature is 20. The wall area is 10 meters square. Find the rate of which is Q of the transfer. And from the previous formula, we know that our Q is Ka into bracket T1 minus T2 divided by X for a plane wall, please. So, and we have all of these parameters. So all we need to do is input them and get what our Q is. So let's move to our next question. A concrete wall transfers heat as a rate of 500 watts. It has a thermal conductivity of 1.5 watts per meter Kelvin, a cross-sectional area of 8 meters square, and the temperature across the wall is 25 degrees C. Find the thickness of the wall. So like I said, put it in diagram. So this is what we have. So a concrete wall transfers heat as a rate. So let's say the heat transfer, like it transfers it across at the rate of 500 watts. It has a thermal conductivity of, which is K, 1.5 watts per mK. A cross-sectional area, our area is let's write it. Our area is 8 meters square. The temperature across the material, so temperature across it is 25 degrees C. Please, I forgot to mention, for conduction, your temperature can either be in Kelvin or in degrees. So if you are given in Kelvin, use it directly. And if you are given in degrees, use it directly. You don't need to convert so any of it. So what we have to look for now is the thickness of the wall, which is X. This is what we are asked to look for. So we know our formula, which is Q equals to Ka C1 minus T2 divided by X, which is now equals, what's our K now? Okay, we have our Q, right, which is 500. We have K, 1.5. Should we have area? Yes, 8 meters square. Then our temperature difference, which is 25, then divided by X. So we need our X. That's 500X equals what? So we have 1.5 times 8 times 25. This is 300. Then our X will be 300 divided by 500. So our X, which is the thickness, is 0.6 meter. I hope you understand. So let's quickly run through it. We're given a concrete wall, and they said the heat transfer or the heat rate is 500 watts. Then it has the thermal conductivity of 1.5 watts per meter Kelvin, a cross-sectional area, which is our 8 meters square, and the temperature across the wall. Now they are not talking. This is our inner temperature or the outer. So across the wall, the whole wall is 25 degrees C. So find the thickness X of the wall. So we know our formula, Q equals to Ka C1 minus C2 divided by X. Now is our X that we're looking for. We're giving the rest of our values aside from X. Then we put the parameters given to calculate our X. So let's move to the next question. It says a wall is 0.5 meter thick with a thermal conductivity of 2 watts per meter Kelvin. One side is 200 degrees C and the other side is 50 degrees C. If a point inside the wall is 0.2 meter from the earth's surface, find the temperature at that point. So, like I said, write out the parameter. So let's draw out. So we are assuming this is our wall. So they said a wall is 0.5 meter thick. So that means this is 0.5 meter thickness of the wall. One side is 200 degrees C and the other side is 50 degrees C. And we know that temperature decreases, so we obviously know that the 200 degrees C should be here and 50 degrees C should be here. It cannot be reversed. So C1 is 200 degrees C. Sorry. T1 200 degrees C, which is T2 50 degrees C. Said if a point inside the wall is 0.2 meter, that means this will be thickness from the earth surface. This is the earth surface. If a point inside the wall is 0.2 meter from the earth surface, and this is the earth surface, so let's pick a point. Let's say this is the point 0.2 meter, which is our, now this is the thickness for the point. Find the temperature. So at that point, this is what we are looking for, Tx. So let's say it is Tx, that's the interface temperature. That is what we are looking for. So okay, we're giving our K for the whole wall. So the K is 2 watts per meter Kelvin. So now when you want to calculate the interface temperature of anything, the first thing you calculate is to calculate the heat transfer all through the wall, the flow of heat throughout the wall. And after getting that, you now use your value to get the interface temperature. So Q equals to Ka T1 minus T2, right? For the whole world now, divided by X. So we have, what's our K? 2. We're not giving area, so we'll just keep it. And we're not giving anything to calculate area. So we have 200 minus 50. Then what's our X? 0.5. For the whole wall, please do not forget. And this is going to give us 600 watts. So we can now calculate our interface temperature. We are still using this formula, which is Q equals to Ka. It's now be T1 minus Tx divided by X. T1 minus Tx, not vice versa because it decreases. So T1 minus Tx. So our Q now is 600. Our K is still, the other values are still constant aside from the thickness that changed, that we are moving close. And now because it is close to, it is from the earth temperature, we are using T1, not T2. Do you understand? And we can actually decide to use T2 too. Just that way we are going to use T2, then it's going to give us Tx minus T2. Do you understand? So we are going to be using Tx minus T2. But if we use Tx minus T2, we do not have a thickness to use because we're giving 0, or better still, we are going to use Tx minus T2. Since we know that the whole wall's thickness is 0.5 and just the portion is 0.3. So if you are asked, if we want to use this, then we have to subtract 0.5. But we don't have to go through all that stress. Since they told us to calculate the temperature from the surface, so we are going to be using T1, which is close, which is the temperature of the earth surface. So this is 2 times, what's our T1? 200 minus Tx, right? Then divided by 0 0.0, okay, 0.2 meter. So that will be 600 multiplied by 0.2 equals to 2 times 200 minus Tx. So divide through by 2. This is going to be 300 times 0.2. That should be 150. Okay, so this is 60 equals to 200 minus Tx. So Tx is equals to 200 minus 60, which is equals to 140 degrees C. Now please note your interface temperature. Since this is the temperature, this interface temperature must be, the T1 must be greater than the Tx, and our Tx must be lesser than T2 because this is decreased. Even if it's just a little difference, they should decrease. For example, now what I meant by that, this is 140, 200 is like greater than 140, right? So that means it decreases. 140 is greater than 50, it decreases. So what I'm saying is that we cannot have anything, this Tx cannot be greater than 200, and it cannot be lesser than 50. What I'm just trying, it should be in between these figures. Yes, it should be in between the figures. So let's quickly run over what we've said. To calculate our interface temperature, we have to know the rate of flow, rate of heat that flows through the whole wall. And after calculating that, then we use our formula to get our 140. We are doing C1 minus Tx for this because our point is close to the hot surface. Then our x is 0.2. Then we'll calculate our 140. So let's move to our next question. A concrete wall has a thickness of 0.25 meter and a thermal conductivity of 1.5 watts per meter Kelvin. The temperature difference across the wall is 40 degrees C and the wall has a surface area of 12 meters square. Determine the heat flux through the wall and the total heat transfer rate. So let's write out our parameters. Let's have a vision of what our wall looks like. So it has a thickness of 0.25 meter, right? The thermal conductivity is 1.5 watts per meter Kelvin. The temperature across the wall is 40 degrees C. That's temperature across the wall. It has a surface area of 12 meters square. So we have to determine the heat flux and the total heat transfer rate. If you can remember, our heat flux is the rate of flow per unit area. So that means we have to know our rate of flow. We have our area and we have to know our rate of flow. It's also the total heat transfer rate. So our Q is Ka C1 minus C2 divided by X. This is our temperature difference. So what's our K? 1.5. What's area? 12. And what's our temperature difference? 40 divided by what's X? 0.25. This is going to give us so this is going to give us 2880 watts. So to calculate our Q, use the per unit area would be 2880 divided by 12. This is going to give us what? So this is 240 watts per meter square. Yes, so and that about the question. Let's come again. We were given the thermal conductivity 1.5, the temperature difference 40, the thickness 0.25. We have to calculate the total heat rate and the heat flux. So we calculated this from our parameters. We inputted our parameters. Then our Q, if you can remember, heat flux is total heat rate per unit area. So and we got that. Our area is 12 and our Q is 288. So let's move to the last question on today's segment. A concrete wall is 0.3 meter thick and has a thermal conductivity of 1.4 watts per meter Kelvin. The wall has a cross-sectional area of 15 meters square. Calculate the thermal resistance and the conductance of the wall. So let's write out our parameters. So we have this right as the wall. I said it is 0.3 meter thick. It has a thermal conductivity of 1.4 watts per meter Kelvin. The wall has a cross-sectional area of 15 meters square. Calculate the thermal resistance, which is our I, and the conductor of the wall. If you can vividly remember, the formula for thermal resistance is X over Ke. So which is, what's our X? 0.3. What's our K? 1.4. And what's our area? 15. So this should give us 0.3 divided by 1.4 times 15. So we have 0.0143 degrees C per, and our conductance is 1 over R, which is equal to 1 divided by 0.0143. 1 divided by answer 70 degrees C. And guys, that is the end of conduction tree plane 1. So in your conduction tree plane 1, you can be asked to calculate your heat transfer, which is your Q. You can be asked to calculate your heat flux, which is your small q, that's heat per unit area. You can be asked to calculate your interface temperature. You can be asked to calculate your resistance, thermal resistance, or conductance. And we've covered all of that. And that brings us to the end of today's teaching. Guys, please do not forget to like, subscribe, share these videos to your departmental mates and people that you know that they are going to need this video. If you have a question, don't forget to drop your question in the comment section. I'll be right there to answer all of your questions. Next time, see you guys later. Bye.